guys, welcome back to my channel. Let's now talk something about some definitions, because as we proceed with this journey we're discovering what all these things are about: subatomic particles, the quarks and the bosons, Higgs bosons, which we specifically going to talk about Higgs bosons first, but we also we're gonna generally talk about bosons, and bosons have a full integer spin from the previous video, right? And we have the examples of this which I gave you. Now before we proceed, I'd like us to have some definitions about some terms which we run into quite often as we proceed in this journey of discovering more and more about subatomic particles, right down to the pions, okay, to the fields, and what are the fields, to the symmetries and supersymmetries that make up the universe, and how they interact, the weak force and the Higgs bosons, how they interact and give mass to particles, to everything, right? That's why it's called God particle. So we're going there. So now let's just define some things about, for example, what is spin in physics. Sorry, some people are washing things outside, so I can't help it. I mean, the sound coming, I don't know whether it will interfere the video, but bear with me, bear with it. Now, what is a spin in physics? A spin, when I'm talking of integral spin or half integer spin or full integer spin, what do we mean by the word spin in physics? Now, it's defined as spin in physics is the amount of angular momentum. Now, what's angular momentum? You know, these are terminologies that we run into quite often, and I want to clean this board and try to give some period of demonstrations about this kind of terminologies that we're having. Yeah, man. So I'm gonna write this cycle here, okay, and give something like this, and give some angle here, maybe let's say 30. Say angular. Yeah, man, this is angular, and this thing may be going around like this, going around like this. We have the momentum. I don't know whether I spelled it right, but momentum constitutes mass of something, an object in motion. That's a momentum. So we have the angular, this that is making as it's rotating. So that's what we call angular momentum, right? So let's now go back and try to understand this thing about spin. So spin in physics, comma, the amount of angular momentum associated with a subatomic particle or nucleus. So I've shown you what is angular momentum as it cycles around. And today I don't have something to show you this, and it's measured in multiple units called the Dirac. It's called Dirac. The units used to measure it is called Dirac. Let me write it down, so guys, so that you can see it. Dirac. These are the units used to measure this thing. H, Dirac H. This is H. This is how I write H. Dirac all H bar. H bar equal to the Planck constant divided by 2 pi. You know what's Planck constant? I want to give you what is Planck constant, don't worry, but just take it that way. It's equal to the Planck constant divided by something called 2 pi. You know what is pi? How to find the circumference of a circle. 2 pi. Right? 2 pi. You know the value of pi? So that's maths. Planck constant is, now I'm gonna give you the value of Planck constant. So please take note of these terminologies because it will be easier for you to understand as we go on. When I say spin or angular momentum, what do I mean? So now let's give the Planck constant. And by the way, I'm gonna tell you what Planck is. So this is very important because this is what will make you understand particle physics so well when you know these things. So the value of Planck constant, before I tell you, okay, let's say first of all, what is a Planck constant? What is a Planck constant? A Planck constant, symbolized as h, is symbolized as h, is a fundamental universal constant that defines the quantum nature of energy and relates the energy of a photon to its frequency. Let me repeat that again. A Planck constant, symbolized as h, which I've shown you here, is a fundamental universal constant that defines the quantum nature of energy and relates the energy of a photon to its frequency. So you might be wondering, what is even a photon? Suppose you don't know what's a photon. I don't know whether unfortunately, yeah, in case you don't know what's a photon, so I'm gonna define it to you. A photon is a tiny particle. Don't tell me you don't know particle also. It's a tiny particle that comprises waves of electromagnetic radiation. Waves. You know what's a wave? And this is elementary physics. A wave is something that goes like this. It's a wave, you know. If maybe we have to draw it to scale, and it originates like this. I'm not sure you will, don't worry. Like this, it's a wave, sine wave, whatever. And we have amplitude, we have period. This is period. This is amplitude. The extent at which it can go up and down. Amplitude, period. This is something they call, I think, trough. You see, here it starts positive, it goes down. It's a wave, up and down. Start here, it completes the rotation. It's a period. So we're gonna talk about that. So I'm just trying to define to you what a photon is. I'm getting ahead, but I just wanted you to make sense of what I'm telling you. So I'm defining that, but we're gonna go there. So that's what a photon is. It's a tiny particle that comprises wave electromagnetic radiation. Let's stop there because I'm gonna talk about it as we go on. And sorry, I'm just looking at the time. And by what is time? Time is relative. Let me not confuse you. According to Einstein, right? So and relates the energy of a photon to its frequency. You know what's the frequency? Up and back and forth, right? Back and forth. It's called frequency when something going back and forth in a second maybe, which is measured in hertz. So in the international system unit SI, the constant value is, so that is now Planck. we're gonna give you the value of Planck constant. In the national, international, the constant value is, Planck constant is 6.62607015 times 10 raised to power minus 34 joules. I'm going to tell you also what joules are. Hertz. Okay, joule hertz. Or you can say joule seconds, whatever, the way you want to define it. Okay, so we can given it the value, you can see is minus 34, 10 raised to the power minus 34, and times that 6.62607015. That's the value of Planck constant. Now, if somebody asks you what's a Planck constant, Planck constant, symbolized as H, is a fundamental universal constant that defines the quantum nature of energy and relates the energy of a photon to its frequency. So it's all about the energy of a photon and to its frequency, and we know what's a photon. I'm going to tell you also what a photon is as we proceed. So that's why I say this is very important for me to define these terms to you, so that when you proceed talking about Higgs bosons, what are example boson and quartz and all that, these words will pop up all the time, and these things like spin and photons, so that you know what they actually are, if you don't know, because I guess that somebody who's watching this video knows these things. And there are those who are curious, those who want to learn. It doesn't have to be that you know. So now let's define what a joule is. I've told you what's a Planck constant. You can see it's measured in joules, but you don't know what's a joule maybe. So I'm going to tell you what a joule is. A joule is the SI unit, universal also, of work or energy. Joule is SI unit of work or energy. 1 joule is defined as the amount of work done when a force of 1 Newton acts on an object in the direction of its motion through a distance of 1 meter. So I hope you know what Newton is. It's a force of Newton. We measure it in newtons, so when we talk about the forces, so that's what a joule is. A joule is a size, it's a unit of measurement given to work or energy. What is work? When somebody tells you, you go perform that work, or this work has to be performed, it's work. The activity of doing something is work, and there's energy involved in doing it. Okay, so it's simple as that, and there's a unit to measure that. When you are washing clothes, okay, you're doing work, and what's the nature of work you're doing? You are washing clothes, and when you are washing clothes, what are you using? Energy, or even machine, washing machine. That's giving basic examples of work actually, which you know. Even when you are walking, you're using energy. Walking is work, so it goes down to everything that you can just think of in terms of work. So that is what is, we are using the joule, which is a SI unit, universal, to measure it, to measure this. And 1 joule, the name joule should not confuse you, it's just given to define the units. So the 1 joule is defined as the amount of work done. It's the amount of work done. Amount is very important here. Amount of work done when a force, what is a force, for example? If I have these things, I don't know how best to illustrate this. Let me say I'm holding a book like this, and this pen is lying here. Then I push this pen, I'm applying some kind of force, and you see that the pen is moving forward. I mean, it can't move on its own, but I'm pushing it. And what am I using? Force. Yeah, has some amount of something that makes something happen. Force, when you exert force. Don't force me. That's something else. You just say, don't force me to do that. Force is something else. But force, when you apply force to push a vehicle that has stopped in the middle of the road and it can't move, you want to move it away so that the traffic can go. Around 10 people come and push it, give it a push. Now that push is the force that you are giving it out of the road. That's how I can define it. So anyway, I'm going far with it. So a joule is defined as the amount of work done. The amount, the word amount is very important. When a force of 1 Newton, we are not doing about that. Maybe I'll have to define to you as we proceed. What is 1 Newton force? Acts on an object in the direction of this motion, see, through a distance of 1 meter, just 1 meter. That's how it's measured. So yeah, now let's talk about a photon. What is a photon? Already I've told you a bit of it when I was explaining about the Planck constant, but now let's go through it. A photon is a tiny particle that comprises waves of electromagnetic radiation. You know what's electromagnetic. If you don't know, then even I don't know how. Maybe you're watching this and you don't know what electromagnetic is. You have seen magnets all over the place and electricity all over the place. So electric, magnetic, created from electric, is temporarily kind of magnet in that sense, because when you introduce electricity to, for example, an iron, I don't have an iron, let's assume that this is an iron. You know, the electrons, the particles inside there are not well organized. When you put electricity, they become aligned, and that's how magnetism is created, from electric energy. So it's called electric magnetic, right? Radiation is the energy that is given out in a decay process. When it radiates energy, it gives radiate. You know what's radiate in English terms? Giving out. So let's go again. A photon is a tiny particle that comprises waves, which I showed you in the board before, of electromagnetic radiation, as shown by Maxwell. Photons are just electric fields, right, traveling through space. Photons, which you see the light in form of photons. What is it that you are seeing actually? What are you seeing? It makes you see. Without photons you can't see nothing. You'll be like, okay, you'll be in the darkness, you won't see anything. And this is what is being defined here. Photons are just electric fields, electric flow of electrons. Electric means electrons. So photons are just electric fields. You know what's a field? When you go to play cricket or football, you play it in a field. You don't play it on the rooftops or on the road. There is a field where you play the game. Or we are running athletics, unless it's a marathon. There's a field. So field in this sense, we're talking about electrons are there. This is a field, a big field of only electrons. So electrons, and what's electrons? You know, if you go to the atom, you know what electrons is? Electron, proton and neutron make an atom. It's massless, but proton, neutron has some mass and make nuclear. So you see that you can relate down as what we are saying here. So photons are just electric fields traveling. So these fields are traveling through space. Very important. They are traveling through space. So photons have no charge, no resting mass, and travel the speed of light. They travel the speed of light. Actually gonna understand what is really photons. Let's go to the next step and you will really get it. What is light? So we are saying this travel the speed of light. What is light? right? We're going to define it here. Light can be described. Light that you see. Is there light there? Light that you see. You know, human eyes, for example, let's use a human now, not dogs. So dogs may be seeing infrared because they see at night, and cats, they see very well in the dark. Maybe I think the eyes are very powerful, infrared, but at daytime you see a dog is sleeping, maybe it doesn't see well daytime, sorry. So I'm getting carried away. So now, what is light? Let's define it again. Light can be described both as a wave and as a particle. That's duality. We have duality. We have it as a wave, which I showed you in the board. Oh, sorry, I've just cleaned it. You know what's a wave? I've just shown you. And a particle. That's the duality of light. So that's how you can describe it. Now let's go further. There are two experiments in particular that have revealed the dual nature of light. Okay, when we are thinking of light as being made of particles, these particles are called photons. So that's what photons are. When we are thinking of light as being made of particles, then these particles we call them photons. So when I'm talking of what is a photon, so now you understand what a photon is. So this photon now, when we are thinking of light as being made of particles, when we are thinking of light as being made of particles, then these particles are called photons. And now these photons that we are referring to have no charge. They have no charge, no resting mass, and travel at the speed of light, which they are part of, because in that case light is made of duality. One part of it is a particle, another part of it is a wave. So photons have no mass, and each one carries a specific amount of energy. Yeah, of course, light is energy. You bask in the sun and start sweating, sunbathing, energy is there. Okay, that is energy. So I've actually tried to define to you what a photon is, what a joule is, and what light is. This is very important as we proceed in our topics. Now let's come to the final thing here, because the video is becoming too long. Energy. The elephant in the room. Energy. What is energy? In physics, energy is the quantitative property that is transferred to a body or to a physical system, recognizable in the performance of work and in the form of heat and light. Oh, so we know, of course, heat is associated with energy. Somebody shouting, please don't mind. There's heat and there's light. Okay, so energy, whenever you see heat, you see light, you know energy is there. And then it's telling you that it's recognized. That's how it's recognized. So energy is a conserved quantity. So it's a conserved quantity. Like when you talk of potential energy, and it drops like this, become kinetic. So you have to hold it there, otherwise it continue to drop, because gravity is going to take it down. It's another force, gravity. Okay, you can see these forces, how they work together. Potential, kinetic, and gravity. Kinetic in motion, potential conserved here. Or when a fruit is falling, you know, at the right where it's there, up there, it has a potential energy, and if it's ripe enough, now it wanna go down because the tree cannot hold it anymore. It develops kinetically. The motion that takes it down dynamically. You can use dynamic or motion, potential to kinetic, and then there's gravity that is working. There's acceleration. Now it's falling. At what rate? Is it constant, or does it accelerate faster as it falls? So as the relation due to gravity is what, 9.8 something 2 meters per second, is it? You can Google that out. So I'm trying to explain to you energy. So, and energy is a conserved quantity, is conserved in whatever form, and the law of conservation of energy states that energy can be converted in form but not created or destroyed. It can't be destroyed. It cannot be created, but it's only conserved. It can be converted but not created or destroyed. Energy. I've tried to have my hands like this in the previous video. When I'm doing like this, then I'm feeling hot. Hot is coming, and I'm doing work. Energy. I'm using energy. That energy. You understand what I'm trying to say? It can never be created. It can never be destroyed. It's what it is. Is this what we call I'm Alpha and Omega, and I'm the beginning and the end? For those who read the Bible, can you relate here something? What is energy? You can define it. You can say they are electrons. Of course, the electrons. We know what electrons are. They're particles. I mean, they're subatomic particles which make up a nucleus, and the nucleus is made up of neutrons and protons, which have a mass. And these neutrons and protons are made of quarks. Two up quark and one down quark makes a proton, and one up quark and two down quarks makes a neutron. And then we have the gluons or the muons, the mesons, which are made of two. And there's integer half, integer spin, and full integer spins, and so on, and all this subatomic world, like quantum mechanics, right? But after all that is said and done, we still have this question: what is this thing that can never be destroyed? It can never be created, but only can change form, can change to one form or another. We given it a term, of course, we understand it's electric, it's energy. It's energy, yeah. We have potential, we have kinetic energy. We have energy in the whatever. Energy. Anyway, that's what energy is. I think we know what is energy, so let's just leave it at that. Why is the weak nuclear force short range? Oh, that is now another topic. So now it's a sort of nuclear. We have nuclear, strong nuclear force, weak nuclear force. We have electromagnetic, we have gravity. The four forces in nature. So the lines of force from one particle to another by the exposed field. Okay, we know about the Higgs field, which absorbs the lines of force of the weak force from one particle to another, gets absorbed by the Higgs field, and that's why Higgs field gives mass to elementary particles this way. If there was no Higgs field, then this thing would be continuous, and there'd be no universe, there'd be no you, there'd be no me, there'd be nothing, because through this absorption by Higgs boson, mass is given to elementary particles. Without these symmetries being broken, then these things like electrons will not exist. We'll have a continuous field, and then the universe and anything, everything else as we know it, will not exist. And this Higgs field is quite strange, because even if you create a vacuum and remove everything else from a vacuum, everything, and make it totally a vacuum, and even remove the fields, all, still Higgs fields will remain there. It doesn't go. This field is strange. So it gives something called a quantum fluctuation of virtual particles pulsating in a vacuum. This is Higgs. After you take everything else, still something is there in a vacuum, and this something is the Higgs boson, is the Higgs field. Quite strange thing. We know it as a Higgs field. It's a field. So this interacts with weak force, absorbs it, and then give mass to elementary particles. Very, 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 very important. Yeah. And we know, of course, we're going to talk about symmetries in the universe and supersymmetries. What does it imply actually? It implies four symmetries. And they are sometimes called gauge symmetries. Gauge symmetries. So if you ask particle physics, where does it get its name? It gets its name from E is equal to mc squared. Energy is equal to mass times as speed of light squared. And of course, mass we know now. We know Higgs gives mass. Mass is something that has weight and can occupy space. Mass attract each other according to Newton with a force which is equal to their mass state and inversely proportional to the distance between their centers. And the mass in the universe attract each other. So guys, we're gonna leave it there. I was trying to define to you these things so that it's clear when I talk of spin, energy, weak force, when I talk of Planck constant, what's light, what's a photon, joules, so that you are familiar and you know what I'm talking about. So because you'll be in the dark and you not even watch this video, it will not be making sense to you if you don't know this. So now I'm going to talk about Higgs boson that was discovered in Switzerland, Geneva. Is that where it was discovered? Accelerator, hadron colliders, and we're going to talk specifically about the W and Z boson. Then we talk generally about bosons example, and boson is something that has a full integer spin. I've told you that. And the one that have integer spins are protons, neutrons, and so on, and quarks. So okay guys, thanks for watching. Please stay tuned, like, share, and comment. You are welcome to come again and again. Please come again and again. Bye for now. See you in another one. Bye.